Hello and welcome to the course in Engineering Mechanics of Materials, often referred to as Strength of Materials in Engineering. And this will be a brief introduction to your instructor and a review of statics or engineering mechanics so that we can be refreshed and ready to solve problems in the course. Your instructor is Professor Douglas J. Leifer, and I hold a PhD in Civil and Environmental Engineering from Tufts University in Boston. I'm also a licensed professional civil engineer in the state of Maine, and I have a professional geologist PG license in several U.S. states, as well as being a fellow of the American Society of Civil Engineers. So let's get started with a basic review. Here you see the different types of beams that can be supported as shown on the right, either cantilevered, simply supported, overhanging, continuous supports, fixed-ended, or cantilevered and simply supported at the bottom of the lower right figure. On the left in the table, you can see the different types of supports and their icons that represent the support types. So the first one is a roller support, and that's represented by the icon shown, and you can see that in the simply supported beam at the right end of the beam. You can also see the roller supports in the overhanging and continuously supported beams. And then at the bottom, cantilever simply supported, you can see the roller support on the right end of the cantilever, the free end. So those support vertical loads, and they're shown in mechanics of materials as vertical reaction forces. The second type of support is pinned, and you can see that's represented by the triangle. And if you look at the simply supported beam on the right, the second illustration down from the top, on the left end of the beam is a pinned support, and that resists both vertical and horizontal loads and results in horizontal and vertical reaction forces. Next, you see a fixed support, which is cantilevered, and that will support different types of loads, horizontal, vertical, and moments. So the reactions are going to be horizontal, vertical, and moments. And then lastly, the simple support, which is vertical loads only and vertical reaction forces. So you often see them drawn as shown here. With example A, the cantilever has a fixed support and it has a horizontal resisting reaction, and that's F sub H, and the convention is to the right is positive. And then a vertical reaction, F sub V, with the convention being up is positive, and then a moment with the convention that counterclockwise is positive. And then in the second illustration, letter B, underneath the roller bearing, you have only a vertical support, and again, the convention is up is positive. And then on the far right, you have a pin, or hinged as it's sometimes called, and you have both horizontal and vertical reactions. So let's get started with a more basic diagram to determine the tension in three chains that are supporting an engine block from a car. For this example, we go to the whiteboard and we're going to note that the engine is in equilibrium. And that's important because once we know this, the engine block is not accelerating upward or downward or to the right or to the left. So if it's in equilibrium, that means that the sum of all the forces, net forces, is going to be zero, and that's true for both the x and y direction. So let's note that, and we can start by drawing a free body diagram. Now let's also note that the engine block itself has a weight of W, and that's usually expressed in newtons. So we'll do this problem in the SI system. So the free body diagram, FBD, for this problem is in two parts. The first part is the engine block itself, W, and then the tension in chain T1. So we can see by inspection that T1 is equal to W. So let's put a box around that because it's part of the solution. We're trying to solve the tensions in each of the three chains with respect to W, since we don't know the actual magnitude of W, so we'll solve with respect to W. The second free body diagram would be the ring. So here you have T3, and we know that this is a 60-degree angle, so by symmetry this is also a 60-degree angle. And this vector component here would be T3 cosine of 60 degrees, in degrees, not radians. And then the vertical component of T3 would be T3, and that would be sine of 60 in this case. And then we would note that T2 is the other horizontal component coming from the ring, which is in this direction, and that's still an unknown. And then we have T1, back to T1 in the vertical direction. All right, so those are our free body diagrams. There are two of them, and we have to solve this problem sort of simultaneously. So we already have the solution here for T1. We want to solve for T2 and T3 in terms of W. So we need a calculator, and we know that the cosine of 60 degrees is going to be 0.5, so we'll simplify that. And we know that the sine of 60 degrees is going to be the square root of 3 over 2, so we can express that as 0.866 if we wish, right? It's also the square root of 3 over 2. So now we're ready to set up some equations. We know that F net is 0, so that would mean that Fx is 0, and here's your positive convention upward. And that means the sum of the forces in the y direction, sorry, that should be horizontal. Let's go back. There we go. And the sum of our forces in the y direction, now up is positive, is also 0. And there's no moments to worry about with this problem. So knowing these equilibrium conditions, we can solve the problem now. So if we look at the free body diagram, we'd like to, let's start with the x. So the sum of the forces in the x direction. We know it's equal to 0, and we know that the convention to the right is positive. So we have 0.5 T3, that's going to be positive, minus T2 is equal to 0. So that means 0.5 T3 is equal to T2. Okay, and then that's as far as we can go in the x direction. Then at the same free body diagram, we have 0.866 times T3 upward minus T1 is 0. So that means that 0.866 T3 is equal, moving this to the other side, is equal to T1. All right, so now we have some expressions and we want to solve the problem simultaneously. So we'll do that now. If we know that T1 is equal to W from this left free body diagram, and this expression 0.866 T3 is equal to T1, so we can just simply replace that with W. And we will then move our screen up a little bit to work more easily. So we can say that T3 is equal to W divided by 0.866. And if we use a calculator for that, that's 1.15. So that means that T3 is equal to 1.15 W. And let's just put a box around that. And then lastly, we want to solve for T2. Well, we can do that now since we have our information. 0.5 T3 is equal to T2. So just divide this expression by 2. So we're going to divide that by 2 and we get 0.577. So T2 is equal to 0.577 W. And we've solved the problem in terms of W. Here's T1 is equal to W, T2 is equal to 0.577 W, and T3 is equal to 1.15 W. Okay, so in practical applications of such a problem, we would then inspect this and say that we have perhaps an engine that might weigh 1,000 newtons, for example, and we would know that we would have to have chains to support that engine, and a ring, of course, too. And the tension in chain 1 would be 1,000 newtons, T1. The tension in chain 2, which is attached to the wall on the left, would be about 577 newtons. And the tension in chains 3 would be 1150 newtons. So you would have to buy a chain that would support at least 1150 newtons at a minimum in order to use the same lengths, the same chain for this diagram for this problem. Okay, we're going to go on to another problem. In this problem we have a simply supported beam. So here you have the roller support on the left at point A and the hinge or pin at point B on the right, and then you have two loads. You have a distributed load of 1 kip per foot for 50 feet, excuse me, and then you have a point load of 10 kips located, it looks like 75 feet to the right of point A. So what we want to do is find the reactions at point A and point B. And if you recall from the discussion a few slides previously, the reaction at point A will only be vertical, and the reaction at point B could be vertical and horizontal. But we have no other horizontal loads on this beam, so that will be 0. The horizontal reaction at point B, or B sub x, was going to be 0, so we can ignore it. So we only need AY and BY for support reactions. So let's go to the whiteboard for this solution. And here we can work on the problem. So we're going to first take a look at the beam, and we realize it's 100 feet long and we have our load. So the first thing we want to do is replace the distributed load of 1 kip per foot over 50 feet with an equivalent point load. So 1 kip per foot times 50 feet would be 50 kips, and we want to put that load, I'm going to redraw the beam like so, and this is how I will draw beams with supports going forward. We want to place that load exactly midway or halfway between the start of the distributed load and the end of the distributed load. So that's going to be a 50 kip load located 25 feet from point A. Like so. And then we have our 10 kip load already shown, so we don't have to move that, and that's going to be 25 feet from point B. Okay, so we have two loads and they're both vertical and we have no horizontal load. So we simply want to find AY and BY, which will be pointing in the positive vertical direction. So we don't have to worry about the sum of the forces in the X direction. So we can note that the sum of the forces in the Y direction, the beam's in equilibrium by inspection, is 0. And here's the convention, up is positive. So we have a total of 50 and 10, so that's 60 kips of vertical load. So that means that whatever A, Y, and BY are, they have to also sum to 60 kips. So we can sum moments now to solve the problem. And if we sum the moments around A, so let's take a look at the moments around point A, and we're going to assume that counterclockwise is positive by convention, CCW. And we know that that's equal to 0, so let's just set this up so that our 50 kip load at 25 feet, the arm of the load is 25 feet. So 50 times 25 is going to create, if I could use a different color pen for this, it's going to create a clockwise moment around A, and so that would be negative. And then we know that our 10 kip load at an arm of 75 feet from A is going to also create a clockwise moment, so they're both negative. And then we know that the support reaction at B is located 100 feet from A, and that's going to create a counterclockwise, which will be positive moment around A. So now we can solve our problem. We'll go back to our black pen, and we will note that minus 50 times 25, and again this is going to be foot kips, right? Minus 10 times 75 foot kips, All right, plus 100b is 0. Okay, so those are our moments around A. Let's clean that up a little bit to make it a little more legible. Plus 100b is 0. All right, so we could say then that 100b, simplifying algebraically, is equal to 50 times 25. I'm moving it to the other side of the equation, is 1250. That's this. And then this is 750 plus 750. So it looks like we can do much of this without a calculator. So this is 2000. So you have 100b is equal to 2000. So b is going to be 2000 divided by 100. So that will be 20 kips. And that's by. And then we also said that ay plus by have to sum to 60 kips for equilibrium conditions. So ay then by inspection is going to be 60 minus 20, which is 40 kips. And the problem is solved. Okay, our next problem is a triangularly increasing, linearly distributed load in an overhanging beam. So this one is a multiple choice exercise, so we can check our work. And we're going to solve this problem using Excel. So I'm going to bring up an Excel sheet that we can take a look at. So in this problem, we'll create an Excel sheet, and we can work with the sheet interactively. So we can enter in the lengths shown from the pinned end at A to the roller at B as 9 meters, and that's in these cells. And you only want to enter in the value, the magnitude. You want to put the units in a separate column. Okay? So then from B to the end, to the right end, the overhang part is 6 meters. And then the span length is just the sum of those two cells. 9 plus 6 is 15. Now the loads. So we're going to break this down because it's triangular, increasing linearly, starting at 100 and ending at 150. We can say that there is a rectangular load starting at 100 at point A and uniformly distributed across the 15 meters of span of beam. So that's a constant. That would mean that if we subtract that 100 from the maximum of the triangularly, linearly increasing load, that we would start that triangular part at 0, because we've subtracted one. Basically, we're starting here at this point here. We're starting at 0, and we're increasing only to 50. Okay, 100 minus 100, and then 150 minus 50. So that's W sub 2 at the origin, which is point A, and then the maximum would be 50. So we've broken it down into two loads that we can work with. All right, so if we have the rectangular load only, and starting at 100, ending at 100, across the 15 meter span, the equivalent point load would be 100 Newton meters times 15 meters, which is just simply these two cells right here. And that's going to be 1500 newtons. And where are we going to put it? Well, we'll put it exactly halfway or midway between the left end of the beam and the right end of the beam. So it's going to be located at 15 divided by 2, so that should actually be changed to 7.5 meters. It was rounded in the sheet. Okay, so it's halfway across the span. And then P2, which is associated with this triangular increasing load starting at 0 and ending at 50, because we subtracted out 100 from both ends, that's going to be replaced with a point load of 375 newtons. How do we get that? Well, what we do is we take the length of the span across which that load runs, and then we multiply it by the maximum value, but then we have to divide by 2 because it's a triangle, essentially a half of a rectangle. And then where do we place it? Well, by convention, you place a triangular load 2/3 from the start of the load, towards the end. So that's going to be 2/3 of the distance, which since the entire span is 15, 2/3 of that is 10 meters. So it's 10 meters from A, that's important. And the location of the point load that we evaluated in the previous part of the problem is 7.5 meters from A to the right of point A. Now we can sum moments. And so our moment around A from these 2 point loads is going to be 1500 times 7.5. Well, that's going to create a negative or a clockwise moment, but I have it as positive here so that we can just simply sum and divide. And then the other point load is going to be 375 times its location at 10, and that's going to create another positive or negative or clockwise moment. So if you add them up, you get 15,000 Newton meters. And if we just simply divide by the span from A to B, then that would give us 1667 for the support at B, and by evaluation of the forces being in equilibrium so that our F sub y is going to be 0, you've got a total of 1500 plus 375 downward, so that's 1875, right? So these two loads have to sum to 1875. So this would just simply be 1500 plus 375 minus 1667, or 208. So the answer here is option A. In this next example, we want to calculate the moment of the 200 Newton force about point A. And this is a frame, and you can see that the 200 Newton force is applied at an angle, and the dimensions are given, and A is cantilevered. So let's go to the whiteboard for this example. Now, the first thing we can look at is a 200 Newton force at this 345 configuration would look something like this. So here's 200 newtons, and you have the configuration of the angle at which it's applied in a 345 triangle. Well, I think the easiest way to solve a problem like this is to note that if this is 200 newtons and you have a 345 ratio, so 5 into 200 is 40. 5 times 40 is 200. So that would mean that this vector component would be 4 times 40, or 160 newtons, and that this vector component here would be 3 times 40, or 120 newtons. So you're scaling up the triangle. In other words, a 3-4-5 triangle is equivalent to, in its ratios, is equivalent to a larger triangle of 120, 160, 200. They're the same proportions. So now we can draw a free body diagram that's a little clearer, and we'll do that down here. We will draw the wall. Here's the wall, and here's the beam, and we're just going to draw it as a simple beam like so. And this is 4 meters, and this is 2 meters, and our forces applied, okay, are going to be 160. I'll see if we can move this diagram up a bit. (120). Those are the vector components. All right, so those are vector components, and their resultant is 200 newtons, so we don't have to include that. So now, if we're summing the moments around point A, we'll go to a different color pen for this. We want to determine the moments with respect to the plane of A. So how are we going to do that? Well, we can look at the arm of the force applied and calculate and sum our moments. So we're going to say the sum of the moments around A, and the convention is counterclockwise, is positive, like so. It's going to be equal to 0. We know this. So what do we have? We have, if we look at what's passing through A, we have 120 newtons times 4, and that's going to create a positive, a clockwise or a negative. So that's going to be minus 120 times 4 meters, and that's Newton meters, right? And then our other moment here is going to be a result of this 160 Newton vector component, and that's also going to create a clockwise or negative moment around point A. Here's point A on the left, right? We don't have any other points to evaluate. So that would be 160, and its arm is 2. So minus 160 times 2. Okay, and we know that that's going to be equal to the moment at A, right? So what we're trying to solve here is moment at A. So this is plus the moment of A equals 0, right? So then in that case we can say that the moment around A is going to be, this is 480 Newton meters, and this is 320. So that looks like it's a total of 800. Okay, this last problem is a problem of determinant analysis, and this is a classic problem in mechanics. For the cable shown, calculate reactions at the supports. And so you have 3 downward red loads shown as arrows here, and we're going to assume that those are 20 kips on the left side, 40 kips in the middle of the cable at the sagging point, and then 40 kips on the right side, the load. Those are the red arrow loads I'm referring to. We want to solve for all the support reactions and then ultimately find AX, AY, and BX and BY, and the dimensions are given. So we're going to solve this problem in Excel also. So we'll bring up an Excel sheet. Okay, so here we're going to set up an Excel sheet, and in this sheet we are going to try to sum all of our moments and solve the problem. So let's start with this row 3. The sum of the forces in the x direction. Well, if you look at, this is 2 pinned supports, left and right, A and B. So it's going to be an AX reaction, which is positive to the right, plus a BX reaction, positive to the right. Equilibrium is going to result in 0. That means that AX, bring the BX over to the other side of the equation, is equal to negative BX. We'll just put that in bold right here. Let's look at the Y reactions. We have AY pointing upward plus BY pointing upward. And then we know that the vertical loads are 20, 40, and 40. Those are given to us and are shown here, but I'm assigning those values. If you add them up, they equal 100. 40 plus 40 plus 20 is 100, but they're pointing down, so that's going to be minus 100 is equal to 0. So that means that AY plus BY will bring the 100 over to the other side, is equal to 100. So let's put in the equal sign for clarity, and we will embolden these two in bold font, and there we go. We've got a couple of different expressions here. Let's sum moments. The sum of the moment around point A, that's the pinned end on the left where the cable's attached to. So that will mean that we've got minus 20 times 20. So this hanging load here, the first load is 20 negative, and it's going to create a clockwise moment around point A, and its arm is 20 feet. So that's going to be minus 400. Then we know that this next load here is 40. So 40 downward at 50 feet from A, 40 times 50 is 2,000. That's also going to create a clockwise moment, so that's going to be negative. And then the last load is also 40. That's this load right here on the right. and that is a distance of 75 feet from A. So that's going to be 75 times 40, or 3,000, also negative, going to create a clockwise moment around A. Then we know that if we add these three up, we get 5,400, okay, negative. So then we will have the support at B, and the support at B in the x direction, or the reaction at B in the x direction, is 10 feet below point A, the top of the pinned support. So that's going to create, if we think about that, that's going to create a negative moment in the Bx at a distance of 10 from A. So that's going to be plus 10 Bx, right? And then we have a By that's also going to create a counterclockwise moment as Bx did. So that's going to be positive. And that is a distance of 100 feet if you add up the total distance horizontally from A. So here's our expression. 5,400 negative plus 10 Bx plus 100 By is 0. So let's bring the 54 over 100 to the other side. We have 10 Bx plus 100 By equals 5,400. We'll put that in bold font. So then we're not done. We have to sum moments mid-span. So let's take a look at that before we can solve the problem. So from mid-span, we have here on the far right, the load pointing downward is 40 kips. So that's 40 kips at a distance of 25 feet. So that's going to create, around mid-span, it's going to create a clockwise moment, which is negative. And then we note that the distance from mid-span vertically is 30 feet up to the top of point A, but we're talking about point B now, summing the moment generated by B sub x around the midspan. So that's going to be 30 minus 10, or 20, and it's going to create a negative or clockwise moment. And then there's a By component that is 50 feet away from midspan, which will create a positive or counterclockwise moment. So that's equation would be here. So you have, in simplification, minus 20 Bx plus 50 By equals 1,000, and bring the 1,000 over to the other side. So we have all of our equations. We have two equations, two unknowns, right? And actually four unknowns, four equations, four unknowns. So we can solve by substitution. So we know that 10 Bx plus 100 By is 5,400. That comes from this line right here. We'll put that in bold again. So we also know that minus 20 Bx plus 50 By is 1,000. So we've got those, right? So we can multiply the top equation by 2 to eliminate variables. So that would mean that 10 Bx times 2 is 20 Bx, 100 By times 2 is 200 By, and 5,400 times 2 is 10,800. So now we have that equation, and then our second equation here was already reiterated. Just simply add them up, and that will eliminate both of, I'll just show that we're adding them here, right? That will eliminate the Bx variables. So we've got 200 plus 50, 250 By is equal to 11,800 kips. And that would mean that By is 11,800 over 250, which is 47.2 positive. So Ay then is going to be, remember in our y direction, the sum of all of our y forces was 100. 20 plus 40 plus 40. So 100 minus 47.2 will give us 58.2. Now that we know By and Ay, we can plug those into the other equations that we solved, or we left as variables above, and solve for Bx and Ax, knowing that Ax is equal to the negative of Bx. So here you have the answer below. Okay, so that's the classic cable problem in statics or mechanics, and solved in Excel. So that concludes the first section of our review, and this is again a review of statics and generally an introduction to getting started to solving problems. And we will solve them both by hand, analytically on electronic whiteboards, and also using Excel, as you saw. And there'll be several examples where we will set up the Excel sheets from scratch, not having any Excel sheets pre-done for you. All right, in this next problem, we're going to evaluate a truss, and we're going to use the method of sections, which you should be familiar with from statics, to solve this problem. And we have a multiple choice here, so that's useful to check our answer. So for this one, for the truss shown, what's the member force in kips? In DI. So that's that diagonal member, DI. And you can see the truss geometry is given and the supports at A and F are shown. And we have 4 downward loads across the truss, J, I, H, G, as shown. Okay, so we're going to go to the whiteboard for this one and do our work there. So here we have our truss, and what we are looking for is the force in member DI. So we're going to take a section, make a cut through members CD, DI, and HI. So I'm going to draw a breakaway part of the right side of the truss with those cuts made, and then we'll come back to that to solve for the force in DI. So we made our cut through members CD, DI, and HI. So the right side of the truss is what remains, and we have a breakaway free body diagram. Now, what we're going to do here is fill in some geometry. So this is going to be 8 feet, and this is 8 feet as well. And we know that our loads at H and G, so I'm going to put them in a different color just to make it easier to view that. The load at H is 16 kips, and that's given. And then the load, downward load at G is 20 kips, which is also given. All right, so there's our geometry of this truss. Now, we also know that the height of the truss from F to C vertically is 6 feet. Okay, so that's kind of important because we do need to know some dimensions of members. So if we take a look at just FDI as a independent force, you can see that it's going to make a triangle, and that triangle will have a base of 8 and a height of 4 feet, and this is FDI here. Okay, so that's a breakaway of that force. Now, how do we get that 4 and 8? Well, the height, that would be, this would be member point D, and this would be H over here, and then this would be down here is I, as you remember from the truss, right? So how did we get the height of 4 feet? Well, you can see that if we go from F leftwards towards I horizontally, you've got 8 feet in the first section FG, 8 feet in the next section GH, and 8 feet in the next section HI. Those are all the horizontal distances, and that's across a height of 6. So basically, if we're going 2/3 of the distance from 2/3 of 2/3, let's draw it this way, 2/3 of the distance from F to I, here's F. We know that that total distance is 8 plus 8 plus 8, or 24, and 2/3 of that is 16. So we're going 16 feet to the left of F to get to H, and then over that entire height was 6 feet from a triangle CIF, if you think about it that way. So we want 2/3 of the height, so 2/3 of 6 is going to be 4 feet. Okay, so that's a triangle that's 4, 8, and then FDI is the hypotenuse. So that's useful to us because then we can start use it to solve the problem. So the first thing we're going to do is take the moments around point F of our cutaway diagram. But in order to do that, we actually have to break down force FDI into FDI in the x direction and then FDI in the y direction. And we can do that now because we know the geometry of the triangle. We know that this angle theta, if we take the, and this is 90, if we take the tangent of the angle theta, tan theta is from SOHCAHTOA, is the opposite over the adjacent. So the opposite over the adjacent here is 1/2 or 4/8. So we want the inverse tangent of 1/2 to get the angle theta. So we'll do that on our calculator, and that's 26.56 degrees. Okay, now that's this angle theta. Okay, so now we could figure out that FDI sub x is going to be, if this is theta, then this is also theta, right? So it's going to be FDI times the cosine of theta, 26.56, and then FDIY, the downward pointing vector, is going to be FDI. So in this case, that's going to be sine. So it's FDI from trig, sine of 26.56. Okay, let's take a pause and calculate those. All right, so those are calculated now, so we can sum our moments around F. Now, we don't actually need the support reaction at F, so that's useful to us. Now, we'll need that in the next example, which is going to be a truss calculation for forces in a member using the method of joints. But this is the method of sections that we're doing now. So if we take the moments about F, then we know that we're going to get, here's F over here. So we could do the simplistic ones first. We have 16 kips and 20 kips, and those are going to create counterclockwise moments, which are positive. So that's going to be 16 kips times the arm from F, which is 16 feet. And then the other one is 20 kips times its arm, which is 8 feet. Okay? And then we have two other things to consider. We have the x and y components of FDI. So let's start with the y component. So the y component is going to be, that's over here, right? That will be pointing down this way. So that's going to also create a counterclockwise moment, so which is positive. So that's going to be this 0.447 FD. Times its arm. Now what's the arm in this case? Well, the arm is going to be 16 feet, right? And then the last one is the x component of this vector here, FDI sub x. And then we calculated that over here, and that arm is going to be the height of the triangle, which is 4. Okay? So that's going to be 0.894 FDI, and that'll also create a counterclockwise moment. So let's put that just over here if we can fit it in, plus 0.894 FDI times 4. And then those are all equal to 0 due to equilibrium conditions. So we can solve for FDI at this point, right? This should be an I over here. So let's calculate that. All right, so we did a little work here. We combined these terms, and then we can see that we're going to have to move the FDI terms over to the other side of the equation, and that makes them negative. So if we then solve for FDI, we get FDI is going to be equal to 38.77 77 kips. All right, and it's negative. So what does that tell you? Well, that tells you that the member is in compression. And so the answer to the problem here would be letter C, okay, which is closest to our calculation. All right, the next example, we'll see the method of joints for a different truss. Okay, in our last example, we are going to solve this truss by the method of joints. So let's take a look at this truss. In this truss, we have a series of forces. We have a 6-kip force to the right, that's positive at node B. We have a 4-kip force at node C at the top of the truss. And then we're given some dimensions in terms of H, the variable H, and 3 vertical downward loads at H, G, and F. And notice that the dimensions are in terms of lowercase h because there is a capital H node with a 24 kip hanging from it near the left side of the truss. So we want to know what's the force in kips in member AH. Okay, we're going to use the method of joints to solve this problem. So we're going to go to our whiteboard for a drawing. Okay, in this example, we're just going to take the moments around point E for the entire structure, for the entire truss. So if we do that, the sum of the moments around E, and we're going to assume that clockwise is positive in this example just to make our calculations simpler. We know that that's 0 for equilibrium conditions, so let's take a look at what we would have. We would have AY times H plus H plus H plus H, so that would be AY times 4H, that's the arm. Now that would make because the support reaction at AY would be vertical, that would make a clockwise moment around point E. So if we use the convention that clockwise is positive here, then this is a positive moment created by AY. So then we have the 6-kip load, and that would also create a positive because it's clockwise by convention here, and that's at a height of h over 2, so that would be plus 6h over 2. Then we have the 4-kip load at the top of the truss, and that has a height or an arm of h, so it's h plus 2, h over 2 times 2. So that's plus 4 times h, okay? Then we have our downward hanging loads, which are going to make counterclockwise moments, so those will be negative. Minus 24 kips times its arm, which is 3h from E. Then we have minus 40 kips times its arm, which is 2h from E. Then the last one at F is 12 kips times h, minus 12h. Okay? And those are all equal to 0 as we've shown. So if we simplify this, we will actually be able to cancel out our h's, and we will get, we'll do the simplification and show you how this is calculated. So we're going to bring all of these negative examples to the other side. So that will leave us with 4HAY. This simplifies to 3. This is 4H, so that's going to be plus 7H is equal to, and we'll bring all the negatives over, 72H plus 80H plus 12H. Okay, so if we bring the 7 over, it'll become negative, so it'll be AY times 4h, and I'm going to put 4h in parentheses. And then we want 72 plus 80 plus 12 minus 7. So that would be 72, using our calculator, 157h. And then simply we can just divide both sides by 4h, so AY is going to equal 39.25 kips. Okay, so let's just use that in our next calculation, which we'll do on the whiteboard. So now we're going to use the method of joints. I'm just going to write this so it's clear, the approach. And what we're going to do is we're going to take point A. Okay, so this will be FAB. This will be FAH. And then we already solved for AY, so we already know that it's 39.25 kips. And then we will have a horizontal component because it's a pinned or hinged end, and that'll be A sub x. Well, if you look at the other horizontal loads here on the truss, you've got 4 kips and 6 kips. So that's 10 kips to the right. So by inspection, this is going to be 10 kips to the left. So that is joint A. Okay, joint A. Alright, so now we can use equilibrium equations. We can say that the sum of the forces in the y direction is 0, and by convention up is positive. So if you look at our y forces, we've got AY, which is 39.25, and this is from our free body diagram here, right? Now we have a y component of FAB, so we'll put this in a different color, like so. FABY. All right. So that one we will have to use some trig to solve that problem. So we're going to draw a little breakaway triangle here, and we'll do that up top here. So we know that here's a triangle, and this would be FAB. And the height of this triangle is h over 2, and then the base is h. Okay, so we want, from this, we want the x and y components of this. Okay, so this looks like a triangle that would be 1, 2, square root of 5 from trig. Okay, so that's useful because then we can go back to our equation and understand that the next term would be the y term of FAB, which is basically going to be 1 over the square root of 5 FAB. So that's essentially the opposite over the hypotenuse here, right, which is the sine of that angle. And if we want the y component of force FAB, it's pretty clear from trig that on statics that we use the sine FAB sine of the angle. The sine of the angle is 1 over the square root of 5. It's the same relationship. Okay, so that's simplified for you, right? And there are no other vertical forces, so that equals 0 at that joint, so that equals 0. So then we can easily solve for FAB, and FAB in this case is going to be minus 87.77 kips. Okay. Now we're going to sum forces in the horizontal direction, F sub x. So now we can work on the sum of the forces in the x direction, and to the right is positive in this convention, and those are 0 due to equilibrium conditions. So knowing that we just calculated this, we can easily solve the problem. So what are the x forces at the joint? Remember, we're solving at the joint A. Okay, so if we sum forces in the x direction, what we'll see is we have, from joint A, remember, it's the method of joints, we have minus 10, right? Because that's pointing to the left from joint A over here. And then we have the horizontal component here of FAB. So we're going to draw that in red also, and that would be this vector, right? So if the vertical component was sine, which was opposite over hypotenuse, 1 over square root of 5, the vertical will be cosine, which is 2 over square root of 5, and that's also going to be in the positive direction, right? Sorry, that'll be this way, okay? My mistake. All right, so that'll be plus 2 over square root of 5 f AB, and we already know FAB, so that's useful. And then we have FAH from the joint here too. And I should redraw that horizontal component as FABX to make things clearer. Okay. And remember, FABX is 2 over square root of 5 FAB. So then plus FAH, and there's nothing else horizontal at that joint, equals 0. So now by substitution we can just substitute this value in, and that looks like FAH, which is the force that we want from the problem, right, is equal to, bring the 10 over to the other side, right, 10 plus 2 over the square root of 5 times FAB, and FAB is minus 87.77. So that would give us FAH calculates out to, I'm going to get the calculator for this. Okay, and I noted a small error in sign convention. So if we bring the 10 over, that's going to be 10 positive, right? If we bring this term over, it'll be negative. Minus 2/5 times a negative 87.77. Okay, so now if we do that, then we're going to have a positive result. So 87.77 negative times minus 2 over the square root of 5, sorry, again, 2 divided by 5 square root, and then we add 10 to that. We will get our answer, and FAH is going to be 88.5 kips. And that was what was requested in the problem. What's the force in member AH? So the problem's solution is done.